In this seventh lecture on Fourier series, we shall discuss Parseval theorem. Actually, Parseval theorem relates the average value of the modulus square of the function, that is f of x square dx, from a to b in terms of Fourier coefficients. This is the average value. This is average value. Value of the square of the function, and also it sometimes stands for the completeness. It also signifies the completeness of the expansion. We shall discuss. First, we see that we have a function in defined function f of x satisfies Dirichlet's condition and is defined. F of x satisfies Dirichlet's condition in AB. So we will have the expansion f of x is equal to a0 by 2 The expansion coefficients are given by a0 is equal to 2 upon delta f of x dx from a to b, am is equal to 2 by delta f of x cos of 2m pi x by delta dx from a to b, and finally similar expression for sine of x b of we write modulus of x square is equal to f star f. So we need to define f star. So we write f star of x is equal to a0 by 2 so there may be some confusion, so we keep it n there. So we use the dummy in integer n for f and m for f star, and we assume that a may be complex as well. This is the expansion for us. So we want to calculate this quantity a to b f modulus square dx, which we write integration a to b f star of x into f of x dx. One could do one thing, we can use both the expansion together. That will make the calculation a bit lengthy, but the length of the calculation can be reduced significantly by using tricks. That is, we use expansion for this and keep it as it is. That is to say, a to b for, so it is star a0 star pi 2 plus summation over m is equal to 1 to infinity am star cos of 2m pi x delta plus bm star sine of 2m pi x delta fx dx. So we use the expansion for f star but not for f. Now we will have terms. First we consider this term. So a0 star by 2 is taken out and it is a by b f of x dx. So this term is taken out, it is constant, so this is the integration. For the rest part we use, this is we can take am star out and then we will have a to b f of x cos of 2m pi x delta dx. This is first part, and for the second part we will have summation over m is equal to 1 to infinity bm star is out, and then we will have f of x sine of 2m pi x delta 2m pi x delta dx from a to b. Now we use the earlier definitions. This part, if we see this, this is a0 delta by 2. So this is a0 star by 2 were there, then a0 delta by 2. So this is the contribution of this part. Then summation over m, this is am star were there, and this part, you see that this part is delta am by 2. So this is delta am by 2. And similarly for the second term it is m sum 1 to infinity bm star delta bm by 2. So if we take delta by 2 out, this part is half a0 modulus square plus summation over m is equal to 1 to infinity. Delta by 2 has been taken out, so it is am modulus square plus from this it is b m modulus square. So if we want to calculate the average value, this is the left hand side has to be divided by delta, so the average value is 1 upon delta f modulus square dx from a to b. This is the average value of the modulus, and this is equal to half times so this expresses the this expression expresses the average value of the modulus square of the average value of the modulus square of the function in terms of the Fourier coefficient. This is one significance of the Parseval's theorem. Another significance is that if we do not take adequate number of terms, say m ranges from my 1 to capital N, but the capital N is not sufficient enough to express the series adequately, then the right hand side will fall short of the left hand side. So this can also be a check that how much value of capital N do we take, so that the representation of the function on the left by the Fourier series on the right is an adequate one, that is, it is within the range of tolerance. That is another point that it signifies the completeness part. That is to say, the left hand side minus right hand side, the difference must be less than some accuracy level that has to be set forward by the user beforehand. We take an example of use of Parseval's identity. So first we write the Parseval identity and then take one of the example and see what result do we get. So the Parseval's theorem is 1 by delta consider f of x is equal to x defined in the range x less than c greater than minus c. We used this value earlier, and we know that this is, as this is odd, Bn has to be calculated, and the value of Bn was Bn was 2c by n pi minus 1 to the power n plus 1. This is Bn. Now we calculate the left hand side. The left hand side is equal to 1 by delta a to b f modulus square dx. So delta is equal to 2c. This is minus c to plus c, and this is x square dx. Delta is 2c. So this can be written as 1 upon c x square dx from 0 to c. So this is x cubed by 3. So this is c square. This is the left hand side, and the right hand side, so we write 1 by 3 c square on the left is equal to summation over n is equal to 1 to infinity 2c by n pi times minus 1 to the power n plus 1 whole thing square. So this will be 4c square pi square comes out, and we will have summation over 1 upon n square, n is equal to 1 to infinity. Now c square cancels out, or we get summation over n is equal to 1 to infinity 1 upon n square is equal to pi square goes on. This is equal to zeta 2 we talked earlier. So this is another way of using using Parseval's theorem. In the earlier expansion, we considered a function and expanded it, and by assuming special values of c, we can have different series. Another way of getting series is the using of Parseval's theorem, and this enables us to calculate the Riemann zeta. The students are advised to study or use Parseval's theorem for few more simple cases.